In this video, we are going to look at how we can use vector methods to deal with mechanics of situations where the particles or the objects are moving in 2 or 3 dimensions. If we have a system of forces expressed as vectors F1, F2, F3 all the way up to Fn, which are applied to a particle or an object, then the vector form for the resultant force is given by the vector F1 plus F2 plus F3 all the way up to Fn. So the resultant force is simply the sum of the individual forces. So our first example, we've just got to find the resultant force of the system of forces shown in the diagram, giving the final answer as a vector. So first of all, let's number off the 3 forces. So our first force, F1, makes an angle of 57 degrees with the x-axis. So we can resolve F1 as 6 cos 57 in the x direction and 6 sin 57 in the y direction. F2 makes an angle of 18 degrees below the x-axis, so we can resolve F2 as being 8 cos 18 in the x direction and minus 8 sin 18 in the y direction. And finally, we've got F3, which makes an angle of 40 degrees with the positive y direction. So we can resolve F3 as minus 5 sin 40 in the x direction and 5 cos 40 in the y direction. The resultant force is simply the sum of the 3 forces. So we have just got to add up F1 plus F2 plus F3, and that can be done very easily on our calculators to obtain a resultant force of 7.662 newtons in the x direction and 6.390 newtons in the y direction. Now if we look at Newton's second law, so far most of our work has usually been used in the format the resultant force in any direction equals the mass times the component of the acceleration in that direction. And that is really just hiding the fact that Newton's second law is a vector equation. So the resultant force acting on an object is equal to the mass times the acceleration of the object. The resultant force as a vector equals the mass times the acceleration as a vector. And we know that the resultant force acting on the object is simply the sum of all of the individual forces acting on the object. So, example 2, we've got a particle of mass 2 kilograms, which is initially at rest at the origin on the xy plane. It's acted upon by 3 forces, F1, F2 and F3, as shown in the question, where t is the time in seconds after the start of the motion. We've got to find the acceleration of the particle, and we've got to find the velocity and displacement of the particle when t equals 2. Well, Newton's second law tells us that the resultant force is the mass times the acceleration, and the resultant force we know is simply the sum of the 3 forces. So we've got F1 plus F2 plus F3 is equal to the resultant force, and Newton's second law tells me that that must be equal to the mass 2 times the acceleration. So we've got the sum of F1 plus F2 plus F3, which has an x component of 2.4 t squared plus 2.4 plus 4 sine t, and a y component of 0.4 plus 0.8 sine 2t plus 2 cos t must equal the mass times the acceleration, which is 2 times a. Dividing through by 2 gives us the acceleration of the particle. So we've got the acceleration of the particle at time t is 1.2 t squared plus 1.2 plus 2 sine t in the x direction, and 0.2 plus 0.4 sine 2t plus cos t as its y component. Now if we want to find the velocity and the displacement of the particle, then we are going to have to integrate the acceleration to find the velocity. So we know that the velocity is the integral of the acceleration. So integrating first of all the x component of the acceleration, we're going to get 0.4 t cubed plus 1.2 t minus 2 cos t plus a constant. Integrating the y component of the acceleration, we're going to get 0.2 t minus 0.2 cos 2t plus sine t plus a constant. Now we know that when t equals 0, the particle is at rest. So at t equals 0, we've got the velocity is the vector 0, 0, whereas our rule for the velocity is telling us that the velocity is 0.4 t cubed plus 1.2 t minus 2 cos t plus c1 in the x direction, and 0.2 t minus 0.2 cos 2t plus sine t plus c2 in the y direction. So 0, 0 must be equal to 0.4 times 0 cubed plus 1.2 times 0 minus 2 cos 0 plus c1 in the x direction, and 0.2 times 0 minus 0.2 cos 0 plus sine 0 plus c2 in the y direction. And that very rapidly tells us that c1 must be equal to 2 and c2 must be equal to 0.2. So the velocity at any time is given by 0.4 t cubed plus 1.2 t minus 2 cos t plus 2 in the x direction, and 0.2 t minus 0.2 cos 2t plus sine t plus 0.2 in the y direction. So when t equals 2, if we just insert t equals 2 in there and use our calculator, we're going to get the velocity when t equals 2 is 8.432, 1.640. Make sure you're using radians for your angles measurement on your calculator. To find the displacement of the particle when t equals 2, we're going to need to integrate the expression for the velocity. So, to obtain the displacement relationship, we've got to integrate, first of all, 0.4 t cubed plus 1.2 t minus 2 cos t plus 2. And that's going to give me 0.1 t to the 4 plus 0.6 t squared minus 2 sine t plus 2t plus a constant. And then we've also got to integrate the y component of the velocity, which was 0.2 t minus 0.2 cos 2t plus sine t plus 0.2, which integrates to 0.1 t squared minus 0.1 sine 2t minus cos t plus 0.2 t plus a constant. Now again, we need to find out what the values of the two constants are, and we know that we're measuring the displacement away from the initial position. So when t equals 0, the displacement away from the initial position is simply 0, 0. So we've got 0, 0 must equal, first of all, looking along the x component of the displacement, we've got 0 plus 0 minus 0 plus 0 plus c3. So that's going to tell me that c3 must actually equal 0. And looking at the y components, we've got 0 must equal 0 minus 0 minus 1 plus 0 plus c4. And that tells me that c4 must be equal to 1. So we know c3 is equal to 0 and c4 equals 1. So we've now got our expression for the displacement at time t. And if we insert t equals 2 into this, then we get the displacement when t equals 2 is 6.18 in the x direction and 2.29 in the y direction. Now moving on to looking at momentum and impulse. Suppose we've got a particle of mass m which is moving under the influence of a single constant force given by the vector p, and suppose furthermore that t equals 0, the velocity of the particle is given by the vector u, and at time t, capital T, the velocity of the particle is given by the vector v. Then, if we use Newton's second law, we know that p, since it's the only force, is equal to the mass times the acceleration. And using the constant acceleration equations, we know that the final velocity and the initial velocity are linked up by the equation v equals u plus at, which can be rearranged to give us the acceleration is 1 over t times by v minus u. So we can rewrite the Newton's second law equation as p equals m over t times by v minus u. If we multiply each side by t, p times t equals m times v, take away m times u. Now, m times v is the final momentum of the particle. So momentum is a vector quantity, m times v is the final momentum of the particle, m times u is the initial momentum of the particle, and p times t is the impulse of the force p acting over the interval of length t. So we've got the momentum of a particle of mass m moving with the velocity v is m times v, and we have that the impulse of acting on a body over an interval of time gives us final momentum minus initial momentum. In other words, gives us the change of momentum of the body. So in example 3, we have a particle of mass 0.8 kilograms is moving with initial velocity 2 minus 7 when it receives an impulse of 1.6. We have to find the velocity of the particle immediately after the impulse, and we have to find the change in the kinetic energy of the particle. So we know that impulse gives us change in momentum, which is the final momentum minus the initial momentum. So we've got 1.6 must equal 0.8 times the final velocity, v, minus the initial momentum, which is 0.8 times the initial velocity, which is 2 minus 7. Which means that 0.8v is equal to 4 1.6 add 0.8 times 2 minus 7. In other words, 5.6 minus 4. So we've got 0.8v equals 5.6 minus 4, which means that v must be 7 minus 5. The initial velocity was 2 minus 7, which means that the initial speed is the square root of 2 squared plus minus 7 squared, which is root 53. The initial kinetic energy, therefore, is going to be a half times by 0.8 times by 53, which is 21.2 joules. The final velocity was 7 minus 5, which means that the final speed is the square root of 7 squared plus minus 5 squared, which is the square root of 74. So the final kinetic energy is going to be a half times 0.8 times the final speed squared, which is 74. So we've got a final KE of a half times 0.8 times 74, which is 29.6 joules. The change in KE is the final kinetic energy minus the initial kinetic energy, which is 8.4 joules. The next example, we have a ball of mass 300 grams hits a bat at 15 meters per second and leaves the bat at a speed of 12 meters per second and an angle of 30 degrees to the initial direction. We've got to find the impulse that the bat exerts on the ball. So, initially we've got the ball approaching the bat. So that's my initial diagram. And if we set up the x direction to be precisely the direction of the initial motion, then we've got the initial velocity is just 15.0. Whilst the ball is in contact with the bat, it receives an impulse from the bat. We don't know very much about that impulse at the moment. We'll just call it J. It's a vector. And then afterwards, we know that the ball is moving at a speed of 12 meters per second at an angle of 30 degrees to its initial direction. So we can write the final velocity as a vector in terms of our x components and y components. We've got a component of 12 cos 30 in the x direction and a component of 12 sine 30 in the y direction. So now we can apply the impulse equals change in momentum equation. So the impulse J is equal to the final momentum minus the initial momentum. The final momentum is 0.3 times v, and the initial momentum is 0.3 times u. So we've got the impulse J is equal to 0.3 times the vector 12 cos 30 12 sine 30 minus 0.3 times the vector 15.0, which gives us as our final answer the vector minus 1.38, 1.8. So the impulse has got a component of minus 1.38 in the x direction and a component of 1.8 in the y direction. Now, if we have collisions between two particles, then we know from our work earlier on in this module that we can apply the conservation of momentum. And this applies as a vector equation as well as just being a single direction equation. So if we've got a collision between two particles which aren't moving in the same direction, then initially we've got a situation like this, when the particles collide, the grey particle will exert an impulse on the black particle, and Newton's third law tells us that the black particle will impose an equal but opposite impulse on the grey particle. So, after the collision, we will have the black particle moving off with a new velocity v2 and the grey particle moving off with a new velocity v1. So, as we've said, the left-hand particle pushes the right-hand particle with an impulse J1. Newton's third law states the force and hence the impulse of the right-hand particle on the left-hand particle is equal and opposite to the force and hence the impulse of the left-hand particle on the right-hand particle. So we've therefore got J2 must equal minus J1. Now if we apply the impulse equals change in momentum equation to the right-hand particle, then we've got J1 is going to be the final momentum of the right-hand particle minus the initial momentum of the right-hand particle. So that's J1 equals m2v2 minus m2u2. And if we apply impulse equals change in momentum to the left-hand particle, then we've got J2, which is the same thing as minus J1, must equal m1 v1, the final momentum of the left-hand particle, minus m1 u1, the initial momentum of the left-hand particle. So taking these two equations that we've just talked our way through and adding them, we're going to get J1 plus minus J1, in other words, naught, equals m2v2 minus m2u2 plus m1v1 minus m1u1, which can be rearranged to give us m1u1 plus m2u2 must equal m2v2 plus m1v1. In other words, the total initial momentum must equal the total final momentum. So what we've just shown is that the conservation of momentum as a principle still applies even if the particles aren't moving along the same straight line. So the conservation of momentum says if a system of particles is moving in such a way that no external impulses act, then the total momentum of the system is conserved. So if we have an object of mass 1,000 kilograms travelling at 20 meters per second due east, and it collides with a second object of mass 800 kilograms travelling at 40 meters per second in a northwesterly direction, and if these two objects move as a single body after the collision, we're going to try and calculate the initial velocity of the combined object and also the kinetic energy lost in the collision. And we're going to have to state any assumptions made in the course of answering the question. Okay, well, we need a diagram. We may as well set up the axes, x pointing due east, y pointing due north. Before the impact, we have the first object is moving with speed 20 meters per second due east, and the second object is moving with a speed of 40 meters per second in a northwesterly direction. After the collision, the two objects are moving as a combined object moving with speed v. So, if we apply the conservation of momentum, we've got the total initial momentum is first of all 1,000 times the vector 20, 0, plus then 800 times by the velocity of the second particle. Now the velocity of the second particle is 40 meters per second at an angle of 45 degrees to the negative x direction, which means that the initial velocity of the second particle is minus 40 cos 45 in the x direction and 40 sine 45 in the y direction. So that's the initial momentum, and that must equal the final momentum, and the final momentum is going to be 1800, that's the total mass, times by the velocity, which we don't know, it's just v at the moment. If we use our calculators to simplify the left-hand side of the equation, we obtain minus 2627.4, 22,627.4 equals 1800 times the final velocity, which means that the final velocity must be minus 1.46 in the x direction and 12.57 in the y direction. Now, if we wish to find the kinetic energy lost in the collision, we need to find the initial kinetic energy of the system, which is a half times 1000 times 20 squared, plus a half times 800 times 40 squared, which gives us 840,000 joules. The final speed of the two objects is the square root of minus 1.46 squared plus 12.57 squared, which gives us a square root of 160.14. So the final kinetic energy of the particles is going to be 1/2 times by the total mass, which is 1800, times by the speed squared, which is 160.14. So the final kinetic energy that we've got is 144,123 joules. So the kinetic energy that has been lost is 840,000 minus 144,123, which to three significant figures gives us 696,000 joules. Where's this kinetic energy gone? Well, most of it, in the course of a collision between two heavy objects like this, will probably be into heat energy and sound energy, and possibly a little bit of light energy. What assumptions have we made? Well, we've certainly assumed that the particles have a head-on collision. It's not an oblique collision. It's not an oblique collision. In other words, we're basically treating the objects as particles so that there's no rotational motion created by the collision. And the other thing is we've assumed that the mass of the particles hasn't been changed by the collision. In other words, that nothing has fallen off either object in the course of the collision. In our next example, we have a military shell which, whilst it is in one piece, is travelling with velocity 70I plus 15k. It then explodes and shatters into three fragments, P, Q and R. Immediately after the explosion, the velocities of P and Q are known, and we have to calculate the velocity after the explosion of R. Now, since there are no external impulses acting during the explosion, the conservation of momentum is applicable. So we can say that the initial momentum must equal the final momentum of the system. So that's the momentum before the explosion must equal the momentum after the explosion. The momentum before the explosion is 50 times by 70, 0, 15. The momentum after the explosion, well, first of all, we've got the mass of P, which is 20, times the velocity of P, which is 120 minus 25. Then we've got the momentum of Q, and Q has got a mass of 20 and a velocity immediately after the explosion of 80 minus 30 minus 35. And finally, the final component of the velocity of the momentum after the explosion will be the momentum of R, which is going to be 10 times whatever the velocity of R is immediately after the explosion. So we've got this vector equation, which can be tidied up easily. So the left-hand side just tidies up to the vector 3,500, 0, 750 equals 4,000 minus 1,000 minus 600 plus 10v. So, getting the 10v on one side by itself, so taking the vector 4,000 minus 1,000 minus 600 onto the other side, we get minus 500, 1,000, 1,350 must equal 10v. So v must be the vector minus 50, 100, 135. So the initial velocity of R immediately after the explosion is going to be minus 50, 100, 135. Now we know that the work done by a constant force when it moves from A to B is the component of F in the direction AB multiplied by the distance AB. And if we're using vectors, then we can say that F cos theta times AB is the same thing as F times AB times cos theta, which is the same thing as the scalar product of F with AB. In other words, we've got, if we call AB the displacement and signify it by S, then we've got the work done is the scalar product of the force with the displacement. So we've got work done by a constant force is F dot S. The power of a force, we can show that if we have a force, any force of size F newtons, and that it's moving with velocity v, then the power or the rate of doing work of that force is given by P equals the scalar product of F with v. So we've got power equals F dot v. So, for our next example, we have to calculate the work done by a constant force of 7I minus 3J plus 9K as it moves a particle of mass 2 kilograms from 417 to minus 2, 3, 15. And then assuming that no other forces are acting on the particle, we've got to find the final speed of the particle if its initial speed was 5 meters per second. Well, the work done by the force is F dot S. F is the vector 7 minus 3, 9, and S is the displacement as we move from 417 to minus 2, 3, 15. Now in the X direction, the movement is 4 to minus 2, which is a movement of minus 6. In the Y direction, we start at 1, we end up at 3, that's a movement of 2. And in the Z direction, we start off at 7, we've moved to 15, that's a movement of 8. So evaluating the scalar product, we've got 7 times minus 6 plus minus 3 times 2 plus 9 times 8. So that is minus 42 plus minus 6 plus 72, which gives us 24 joules. Since there are no other forces acting on the particle, we can say that the work done by the force gives us the change in the kinetic energy of the particle. So we've got 24 joules is the final kinetic energy minus the initial kinetic energy. We know that the initial speed of the particle is 5 meters per second. So the initial kinetic energy is a half times 2 times 5 squared. And the final kinetic energy is going to be a half times 2 times v squared, where v is the final speed. Half times 2 times 5 squared gives me 25. So I've got now 49 is the value of v squared. So the final speed of the particle must be 7 meters per second. Our final example, we've got a particle P of mass 5 kilograms moving in outer space under the action of just one force F in such a way that at time t its velocity is v meters per second, where v is 3t squared minus 6t in the x direction, 5 in the y direction, and 6 minus 2t in the z direction. We've got to determine the acceleration of the particle and the displacement of the particle from its initial position when t equals 2. Turning it into column vectors, we've got v is the column vector 3t squared minus 6t, 5, 6 minus 2t. Acceleration is the rate of change of the velocity, so we've got a is dv by dt, and differentiating the velocity we get 6t minus 6, 0, minus 2. So when t equals 2, the acceleration is 6, 0, minus 2. To find the displacement of the particle from its initial position, which we usually denote by r, then r is the integral of v. So we need to integrate v to find out what the displacement expression is. Integrating 3t squared minus 6t gives me t cubed minus 3t squared plus a constant. Integrating 5 gives me 5t plus a constant. Integrating 6 minus 2t gives me 6t minus t squared plus a constant. We know that when t equals 0, the displacement away from the initial position is 0. So that means that when I plop t equals 0 into the expression for r, I must end up with 0, 0, 0. In other words, we must have 0 minus 0 plus c1, 0 plus c2, 0 minus 0 plus c3 equaling 0, 0, 0. In other words, we've got c1 equals c2 equals c3, each of which is 0. So the expression for the displacement is r equals t cubed minus 3t squared, 5t, 6t minus t squared. Putting t equals 2 in, this gives me a displacement of minus 4, 10, 8. Now for part B, we've got to find the kinetic energy of the particle when t equals 0 and when t equals 2. Now we know the velocity expression, so when t equals 0, we've got the velocity is 0, 5, 6. So the initial speed of the particle is the square root of 0 squared plus 5 squared plus 6 squared, which is root 61. Which means that the kinetic energy of the particle initially is a half times by 5 times by the speed squared, which is 61, and that gives me 152.5 joules. When t equals 2, we've got the velocity is 0, 5, 2. So the speed is the square root of 0 squared plus 5 squared plus 2 squared is root 29. And the kinetic energy is going to be a half times 5 times the speed squared, which is 29. So we've got a kinetic energy of 72.5 joules. So got the kinetic energy of the particle at the 2 times. Now we know that the work done by the force between t equals 0 and t equals 2 gives us the change in kinetic energy. So we can say the work done by F is the final kinetic energy minus the initial kinetic energy, which is 72.5, take away 152.5, so that is minus 80 joules. The minus sign there means that we're having to do work against F. So in fact, we've had to do 80 joules of work against the force F. Finally, we've got to find the rate at which the force F is working when t equals 2. Now, when t equals 2, we already know that the acceleration is 60 minus 2, and the velocity at t equals 2 is 0.52. We're being asked to find the rate at which the force F is working when t equals 2, and the rate of doing work is exactly the power, which is F dot v. But at the moment we don't know what the value of F is. But Newton's second law will tell us that straight away. So Newton's second law, F is the only force acting, so we've got F is the resultant force, and the resultant force must equal the mass times the acceleration, which is 5 times 60 minus 2. So we've got the force must be 30 minus 10. So the rate at which F is working is the scalar product of 30 minus 10 with the velocity 0.52. Evaluating that scalar product, it gives me 30 times 0 plus 0 times 5 plus minus 10 times 2, which just gives me minus 20. So the rate at which F is working is minus 20 watts, which means that the particle is working against F at a rate of 20 watts. And that concludes our rather long video on using vectors in mechanics.